Good morning. I'm pleased to have an early slot. I wouldn't have wanted to have a late one after all I've heard last night. It was very tiring. So I'm going to start with a couple of disclaimers. In this talk, we're going to talk about functional programming, and we're going to do it with using Scala for examples. So if I'm assuming that you're here because you know a little bit about functional programming, or at least have an interest in it, and you can read Scala or at least follow along with the syntax and so on. I hopefully don't want to lose anyone, so please ask questions if you're not familiar with Scala and anything doesn't look too clear. So I'm going to start with what is one of the big questions of our day, which is function programming and object-oriented programming, how they relate, and in which situation it's appropriate to use each one. Obviously, we most of us will be aware that there's a tension there. There's different things that the two do better. Some do better in certain areas. For example, functional programming is typically easier to reason about statically, to think about the code at before you run it. We have things such as the substitution principle. In Scala, at least, we have a strong type system that we can exploit in various ways, and various other techniques that can help us in forming a model of what's going on. While we probably also know that in many real case scenario, object-oriented code tends to run faster. The JVM is based on, it's written with that in mind. It's typically better at optimizing it, and it's handling state, if you have to handle state in functional programming, is not the most painless experience. So that's the tension, and what a lot of people are wondering is whether there's a way that these two things can be related together, that we can switch back and forth between the two representations, at least in circumscribed areas of our system, and that's what we're going to try to do today. So in this talk, I'm going to introduce a technique, which is a fairly general technique called church encoding. That is a relationship between data and functions that we can exploit to see if in tight performance hotspots we can switch to more object-like representation. So it's not only a technique that relates to performance, but in this case, it's one of its strengths. We're going to try to have everything. We're going to try to keep the nice functional declarative style while having better performance at runtime. And also, we're going to talk about a case study, which is a project that my colleagues and I have done recently. It's been a Seattle-based startup that commissioned us to write a time series analytics engine, and I hope that this as an example is quite fitting to the conference, even though the general topic of functional programming may not be. It was a project with the expectation of high performance. We wanted it to run fast, to be able to process terabyte size data sets in the order of a second. And we obviously wanted to provide algorithms for it that data scientists could use, so provide the API that the data scientists could use. And while keeping everything running smoothly. So now there's some things that we're not going to look at. For example, in order to achieve the performance, we had to make sure that it was possible to go distributed. We're not going to look at how we've made a distribution. Likewise, we're not going to look at exactly how we are going to implement the algorithms, specific algorithms. We're just going to look at how we have sort of reconciled the API and the runtime performance. The most important thing was choosing the right runtime technique in order to get things running. So starting at the top, we're going to actually try to code, look at the code from the ground up of what a time series system is. A very simple time series system. So if you mentally try to represent what a stream of data might look like, you might come up with something like this, with a model of this sort, which if you were asked to map this to an object-oriented mindset, you will probably say the nodes there are objects and the arrows there represent data flow. And for example, we could represent data flow, we could implement data flow as method calls on the objects. So in this case, the nodes 0 and 4, if you can read the numbers, are source nodes where the data comes from. Most of the others are transformation nodes. And finally, we have a consumer node at the bottom. If we were to implement things this way, we end up with what is called a push model of a stream, where the data flows from top to bottom and the data flow is initiated from upstream to downstream. Data is pushed down. The other way that we can represent a stream structure is functionally by what is called an algebraic data type. So who knows what an algebraic data type means? All it means really is a data type that is composed of other data types via and or relationship. For example, our shape can be either a rectangle or a circle. A rectangle has a width and a height, and so on. It's a sort of closed sort of system, closed model of what something can be. And then at the bottom there we have the Scala expression of the same thing. Another typical example is a tree, which I'm sure you all have seen in computer science. Another example of an algebraic data type, and you can notice that we can sort of recurse in our definition of algebraic data types. The node case class, a K class, by the way, in Scala, if you don't know, it's just each of the things that an algebraic data type can be. We can recurse and make various case class contain other instances of tree. So if we were to use this to represent a stream, we would probably end up with something like this. We have we'll proceed from the outside in, if you will, this time. It's the other way around. So we have the consumer, which contains, sort of encapsulate the reference to the upstream node, which then contains a reference to the upstream node, and so on. And this is more like how functions work. In a sense, it's not how function works, but that's how the same way that we think about functions. In order to have a value from at the output will request the next value of the node immediately upstream, and that would then will request the node upstream, and so on. And this is what we call a pull model instead, where data transfer is sort of initiated from the bottom, is requested from the bottom to the top. Have I still got everyone so far? So now obviously writing things like this is awkward. You can easily write convenient methods to translate something like this to something like this in terms of we want a more fluent API, something like this, and this is easily enough done. And you probably recognize in this a resemblance to many other streaming API that you've seen in various other products, I'm sure. So do we right now see any problems with this as we have expressed? If we were to adopt the sort of functional pool style system, can we see any potential issues with it? Well, perhaps things like, if we might want to keep state, it might be awkward. Performance issues might come up. We're going to look at them. We might also have to ask ourselves how easy will it be to add new data types, to add new node types once we declare like a sort of closed form algebraic data type. But let's actually adopt this for now because it has its advantages. And let's try to actually code. Just make something. Let's code something. Let's write an API, very minimalistic API with a minimum of operation to see where it takes us. This is, by the way, where you can get some of the example code. I'll show it to you later if you want. So we're just going to find 4 operations here. Like good functional programmers, the first thing we do is to write down the types that we want our staff to have, and then we let the types guide us towards the implementation. So we have the first piece of our API, which is an introduction form where the data will basically come from, and we simply instantiate our stream from an iterator in this example. For example's sake, obviously in a real-time system, the data will come from either a storage or the network or what have you. But we're happy with the iterator for the time being. Then in the middle, we have two transformation operation. One is what we call a map or a transformation. Basically, we just take a stream of a given type, we combine it with a function that goes from type A to type B, and we, end up with a stream of type B. Similar zip is, all it does is tuples two streams together. While at the bottom fold, we have an elimination term or evaluation term. In this case, we're just going to keep it simple and do a fold. I don't know if any are not familiar with the concept of a fold. It doesn't really matter if it just means applying the same operation repeatedly onto an accumulator. It's not really crucial to understanding the examples. It's just a final algorithm that takes a stream of data and produces one single final result. So now that we have our minimalistic API, let's translate what we just done to Scala, and let's translate it in a way so that we can have that nice API that we have, that we saw earlier. So none of these things are implemented at the moment. They're all still in implement, but just to show the structure. I hope if anyone finds any aspect not familiar with Scala, find any aspect of the syntax confusing, just let me know. Let's go ahead and actually implement these methods and see what we end up with. So this is the first step. And you might notice there's not very much going on yet. All we've done is extend stream into a series of these case classes that do nothing, they contain no code. They simply represent what the operation is. As I said, it's a pure algebraic data type. It doesn't contain any behavior. All we do is, at the end of this, once we've composed our stream, we have a sort of tree, a sort of structure that contains the meaning of the computation, but not means of executing. This is a common pattern in functional programming. which is often called the interpreter pattern. We don't want to mix description and implementation. So obviously, at some point, we're going to have to do something. We're going to have to write something that that evaluates all this stuff. To run it. So how do we run it? Well, one way, obviously, is to, first of all, if we want to get a data, like a data point from a stream, somewhere we're going to have some kind of next method that gives us the next, or function, gives us the next element, so we can actually get the data and do something with it. So that we can implement it for each of these node types is, firstly, what we can do is use polymorphism, just old normal object-oriented polymorphism on each of those things. But as we said, we don't really want to mix description and implementation. We don't want to put the behavior in these case classes. So instead, what we're going to do is use pattern matching to implement a next method. In this case, pattern matching in Scala, if anyone, it's just in a sense, is a switch statement where when we look what something is, and then we do something according. So if our node that we want to get something from is a from iterator, we just, from iterator containing a source iterator, we just request the next element from the iterator. If it's a map or a transform, as you can also think of it as, then we just get the next from the upstream node and apply a function to it. And similarly, we just here, all we do is really following the types, and the implementation comes pretty much by itself. Having a next method, now we can move on to actually implement our fold function, our fold algorithms. Don't get too stuck on this code. I'll just describe it for you. All it does is keep repeatedly calling next and applying the function to an accumulator until we get our result. So so we have a very simple working implementation now, but actually we don't. Can any of you see what the problem with this is? This won't work. The main problem is that we never check that whether the iterator still has data available. That's what happens when we try to request data from an iterator that has run out and has got no more data in it. We get an exception, so this won't work. We need to handle this somehow. So trying to keep in the functional domain. What is the data structure that can tell us, that can describe a value that may be there but may not be there also? That's what in Scala we call an option. In Java 8, I believe it's called an optional. In other languages call it a maybe, or similar. So let's try to rescue the situation. Let's make our next method return an option instead. So now we have our new option, or we do a next method returning not just a naked A anymore, but an A wrapped in an option. This is just the new code as it has to be to adapt to the new type signatures. And similarly, we have to alter our fold algorithm to take advantage of it. So if we try to benchmark this on a moderately complex combination of iterators, combination of stream nodes, we get about 70 million data points throughput on a normal laptop, which is a starting point, I suppose. But we can certainly do better. Can anyone spot where the problem is likely to be with this approach, performance-wise? Well, the big problem here is that performance-wise, option is in fact an object in the JVM, from the JVM point of view, an object that has to be instantiated. It has to be garbage collected, and here we're basically creating one of these for every data point, for every node. So we'd likely be creating a lot of those, and the performance is likely to suffer because of it. So can we improve it? And more importantly, what I mean by improve it is, can we improve this not by just going back and hack things until the performance gets better, but how we got a mental, like sort of mental tool, like a technique, a well-defined technique that we can take advantage of to get rid of this excessive allocation. And this is where we actually get, sorry for being a bit slow to get there, to the point of church encoding. Church encoding, as I said, is a relation between data and functions that basically states that data can be represented as functions and the other way around. If you go on to search for church encoding on the interwebs, you perhaps will come across a Wikipedia page or some other article that will show you a series of barely understandable expressions of perhaps at first sight dubious practical applicability that will claim that it's not necessary to have numbers. We can represent numbers via function calls. Like we can represent functions, numbers with functions. We can also represent various data structures with functions such as lists, tuples, booleans. Let's have an example here. We have a data type, algebraic data type option that can have a sum or none as its possible things that they can be, I suppose. And the church encoded equivalent will be something like this. You have an object that actually has methods corresponding to what your case classes used to be. So it says algebraic data types and interfaces are equivalent. So if I switch back and forth a little bit, this is the object, this is the sort of, ADT representation, this is the church presentation, receiver representation. And another way of saying the same thing is returning an option is equivalent to calling returning something is equivalent to calling something. And obviously by equivalent, I don't mean it's exactly, I don't mean it's the same thing, it's obviously a different thing, but what it's meant by equivalent is that representationally, in terms of the information content of what we're doing, the two things can be made to convey the same meaning. So in a nutshell, case classes as method calls, or returning something equivalent to calling something. So let's try to apply this to our example that we just seen. When you request something, when you request a value, and instead of getting a value back, you get a function calling something else, the sort of flow of command is going the other way around, isn't it? This is also sort of relates to things like callbacks in various contexts. I'm sure like you've all used APIs where that made use of a lot of the callback concept. Is kind of like similar continuation passing style. We, instead of expecting a value to be returned to us, we provide an interface that the receiving object will call with our value. To put it graphically, to put it pictorially, if we imagine applying this to our stream, we have the downstream node. The downstream node initiates things called, he wants the next value. Instead of just calling next, it calls next and provides a receiver to the upstream node. The upstream node, instead of returning a value, it calls the receiver. And the receiver is sort of contained within the downstream node. the good thing is that when we call the value here, the value is not wrapped in option anymore. We just call receiver.sum, for example. We don't have to instantiate anything. Let's have a look how the code changes after these changes in concept. Obviously, we used to have a functional ADT-based API, and now we have something different entirely. It's more perhaps object-oriented, and it's definitely not the same thing. It's two different representations, and we need a way to go from one to the other. Ideally, we want to keep both of them, because both of them had advantages. So in order to go from one to the other, we'll have to do some kind of transformation, which we called compilation in this case. Now, compilation seems like a scary word, but no, let me reassure you that it's, in this case, it's just a straightforward case of substituting one thing with another. It is not a compilation complexity of the order of like an actual compiler. All we do is translating from one type to another. It's something I have to write once, and we're not going to look at the compilation step code explicitly, but you're going to have to take my word for it. You don't have to be scared by this. We can simply it's done easily enough. Don't worry about it. So now our nodes, our stream nodes in this representation become something else. To borrow a term from functional reactive programming, I will call them observables. They still have a next method, and the next method expects this time a receiver. When this next method is called, such as for example during the execution of this algorithm here, next method is called with the reference of the receiver, which is held by the downstream node. As part of this, we can expect the receiver to be called and populated with the value, so then we can check the contents of it and act accordingly. At no point was an object instantiated. In this case, we can write our code in a more performant way. We don't have to do any pattern matching. And let's have a look at an example of one of these concrete implementations of observables. For example, map, just a plain transformation. We have a source observable and a function. So next, does the same thing, calls the upstream observable, passing a reference to the receiver, and then applies the function to receiver. If there is something, if there is nothing, acts accordingly. No allocation here. And as we've noticed, now we're actually using, we're using polymorphism, which is something we didn't want to use before, but we're using it now because this is simply a runtime object. It's a runtime representation. It doesn't pollute our model in any way, so we don't really care. We don't have any guilt in doing it in this case. And we have also obviously state. If we look at the implementation of receiver itself, it's exactly what you would expect. An implementation of the interface, some or none, as per the signature of option, and some variable stuff inside to keep track of what it contains. This is mutable. We have introduced state, but again, we're not too concerned about it in this case. This is all purely runtime stuff. What's more, the state is not observable at all outside of the execution nodes. It's not something that can cause us problems. So again, not a problem, and we certainly gain some performance here. So how is it better after doing this? It seems like we've done a lot of work. How exactly is it better? As we said, we expect it to be more efficient, and it is. We've gained, for example, in this case, which is a very simple example. We weren't trying to sidestep anything major, but we still got a 50% performance improvement from it. In case we have not just an option, but we perhaps want to model all the possible conditions. For example, we might want to model the fact that there might be an error upstream. Some of the upstream nodes might have had, I don't know, any problem at all. Or we might want to model a wait condition saying there's no data now, but there might be later. but don't try again before this long. Then we can sort of, instead of expanding the sort of wrapped data type that we return, such as option or our own custom ADT, we simply expand our receiver with more methods, which is what we did, by the way, in practice. In a way, we had an error methods, we had an await method to signal the fact that there will be data, but just not right now. So we're now able to use more performance efficient coding techniques such as polymorphism, and to keep state without many problems. You will have to keep state at some point. Running some algorithms, running some transformation nodes is never as simple as, well, it's not always as simple as one value in, one value out. And it might be, better even if you want to, only from the point of view of keeping certain values around to improve performance, later. It's, in this case, it's actually a credit to be able to keep state without polluting our model. And we can inline code, we can be dirtier, knowing that this is not going to impact on the essence of our API. So we're going back to what we have seen at the very beginning. At the very beginning, we had like an object-like structure where data was passed downstream via method calls, and now do we not have the same thing that we started with? In a sense, we do. Not exactly the same. We have here data flowing, the sort of chain of command flowing both up and down. Up when the next value is the request for next value is initiated, and down when the upstream node calls the receiver. And this is actually a hybrid control flow. It's a hybrid push and pull at the same time. We've mentioned state. We have introduced state. As you know, function programmers don't like it, but we have also mentioned why it's not an issue at execution time. And the reason why we sort of gone back to what we saw at the very beginning also explains why church encoding is sometimes called refunctionalisation. What we've done at the beginning, taking some functions, we have turned them, we have reified, made them into objects, into case classes in our algebraic data type, and now we're going the other way. We're going back again and making them functions again. So it seems that we've actually done a lot of work to get where we were. You might wonder what we have gained. What was the point of all that? Couldn't we just stay in the object domain and take advantage of that? Well, the good thing is that when you have a neat, tidy function representation, ADT-like representation, is a lot better to reason about, is a lot better to transform, is a lot better to optimize, if we can pattern match over it, if we want to swap things around. And obviously, if you're going to run your algorithm distributed, you're also going to have to split your stream into sort of various ranges, various segments that you can run in a distributed way. And you definitely want to do that while you're handling a easy to reason about, concise ADT representation, not a system of objects. So we have both things available to us at the moment. So this is not church encoding of the whole system. We've only encoded a small part. Church encoded a small part of our system, which is the optionality of our value. It is a partial inversion control in the sense that we don't in the sense that we have a hybrid push and pull model. We don't just pass the whole continuation of our program back. We have avoided a lot of allocation. We introduced state, which is not a problem for the reason that we have seen. And most importantly, what we've gained is we've gained this conceptual model where we can, in the most tight performance hotspots, we can switch back and forth between a more object oriented, like execution model and a more functional execution model. And the bigger picture is that in functional programming, church encoding like scenarios occur quite often, whether wittingly or unwittingly, whether we know that we're using, that it's called church encoding or something else. We do this a lot with Reify, we change back into function. It happens a lot. And recently there's actually been a lot of explicit interest in it. If you've ever read about things such as shallow encodings versus deep encodings, or the tagless final style of domain-specific languages, it's kind of like another way of looking at the same thing. There's quite a bit of literature that you can read about if you're interested, and I'll have it on a slide shortly. But more practical sense, in this case, we've taken advantage of it to gain some performance, which is also probably why, it's probably the application that I suppose many of you will be most interested in. So the concept summary is that there's always a way to represent a data structure through functions and the other way around, and you can exploit it if the need arises. And in this way we have gained this model that we can use to map between the two things. This is some further papers if you're interested in reading it. They are functional programming oriented, but they're very interesting, and they're perhaps not the most accessible. I'm having trouble myself with some of it, but it does start from the ground up, and it's something I found very fascinating. And this is about it. Thank you for listening, and I hope have a good rest of the day.
Thank you, Danielle. Who has the first question? Don't be shy. No? Well, if you are a bit shy, I'm sure Danielle will be happy to answer any questions later on today. Mm-hmm. And I would also like to say, if you have any feedback on the conference, we would love some. Go to our website /survey and give us your ideas or ideas of improvements, etc. And give a warm applaud for Danielle.